Hello guys, so welcome to our first lecture in that course. And we're going to start by Cmos Logic and the logic gates. So Cmos technology is a technology, is a way to fabricate logic gates, okay, out of transistors. So we know from our course in digital circuits, there is what's called the logic gates, which is circuits that do some logic. And we learn it there, three basic logic and or and not. Okay. So in that video, we're gonna explore how, in industry, how to fabricate, what is basically the circuit that can do that. Okay. And it all starts by simple transistors, which is the NMOS transistor and the PMOS transistor. So this is the NMOS transistor. And this is the PMOS transistor. We don't need to know the internal structure. This is part of another course, the analog circuits. But anyways, there is NMOS, there is PMOS. And here are the symbols for both. Okay. So we need just to know what's gonna happen if you put input to the transistor. And since we are talking about digital circuits, so our inputs are, 0 or 1, 0 volt or low volt and the high volt. This 0 volt, this low volt can be 0, can be -1, any voltage that you consider the low. High volt can be any voltage that is, of course, different from the low, and you consider the high. The very famous example is 0 volt and 5 volt. In our course, it's 0 and 1. Okay. So when you put 1 to the NMOS, what happens is that this NMOS turns into a short circuit. And I mean by a short circuit that you can imagine that this node or this terminal is connected to this terminal. Short circuit. And if you put 0, it will be open. So if you put 1, it will be short circuit. If you put 0, it will be open circuit. How about PMOS? PMOS is also affected by the voltage on the gate. Here is the gate. This is this node here, this terminal. But it's the opposite now. If you put 0 here, that will be short. You can imagine it's short. For very low resistance that we can consider as 0. So this is basically short here in that case. And when you put 1, it is the opposite. So this will be open circuit. And from that very simple characteristics, we can build our logic gates. Of course, with some more modified or more complex, but still it's yes complex, but it's still doable. You can solve it easily. And here is our first, and simplest logic gate or logic circuit, which is the inverter. The inverter logic. The inverter logic simply, it inverts stuff. It inverts its input. So we have 2 options for the input. We have just 0 or 1. And the inverter just, negates that. If it's 0, it will be 1 on the output. If the input is 1, it will be 0 in the output. So let's see how. So here is, the inverter circuit. This is called, you can call it inverter circuit. It's a circuit, 2 transistors connected in that way. Okay. And you connect the PMOS here to the ground, and you connect PMOS here, one of the terminals of the PMOS to VCC, or 1, because now, again, in our course, we will not talk about voltages. We will talk about 0s or 1s. 0 is low volt, 1 is high volt. Now let's put 0 and see what's gonna happen. It's an inverter. We should see 1. We should see high voltage on the output. Let's see. So I'm gonna put 0 here. So the two gates are connected. So there will be a 0 here and there will be a 0 here. And just look above here. If you put 0 at NMOS, it will be short. And if you put 0 at the, I'm sorry, if you put 0 at the PMOS, it will be short. If you put 0 at the NMOS, it will be open. So this will be open here. So once you shorted this, so basically you have a path from VCC to Y. So Y will be 1. So when I put 0, I got 1 here. 0, 1. Let's do 1 at the input. If I put 1 here again, the 1 will be reflected here at the gate of the PMOS and at the gate of the NMOS. At the gate of PMOS, if you have 1, it will be open. At the gate of NMOS, if you have 1, it will be short. So now you have a path from Y to the ground. It's like the Y is connected to ground. So you will have 1. I'm sorry, you will have 0. So when I put 1, I got 0. When I put 1, I got 0. That's the inverter. That's the inverting logic. And why is it called CMOS? Although we are talking about NMOS or PMOS, what is the C here? C for complementary, because they complement each other. If one is open, the other is short. If the one is short, the other is open. You cannot find them at the same time short or at the same time open. It will not be a digital circuit. Good. Can we do something more complex? We have been taught before NOT or the inverter and OR logic. Let's see. That's basically the AND gate. So that AND gate. We're gonna discover now. Actually, it's 2 gates, not just 1 gate. But as a whole here, it's an AND gate. Let's check. Looks like you have here two inputs, because there's the AND gate, which has a symbol like this. The simplest has 2 inputs, A, B, and Y here at the output. Let's put 0, 0. I'm gonna put A0. So remember, A here is, you can consider this as connected like this. But we're gonna remove the connection just to make it simple. So you have 0 here and 0 here, B0, B0. 0 at the PMOS is short. So basically you have a short here and you have a short here. 0 at the NMOS, it's open. Again, it's complementary. So when that is short, that will be open. So that point is connected to that point. So there will be 1 here. And what is that? That's the inverter. You don't need to continue, analyzing. You know that if this is an inverter and you have 1 here, you should have 0 here. And that's basically the case. And you can do it, of course, here is 1 and also 1 here. This will be open, this will be short. So why have a path to the ground? Let's have another example. Let's do 0, 1. 0 at A and 1 at B. 0 on the PMOS will make it short. 1 at the PMOS will make it open. Still, we have a path from the 1 to the input here. You don't need even to consider the rest because it will be complementary as well. Let's check. So 0 at the NMOS, it's open. 1 at the NMOS is short, but remember, this is open. So you have a resistance or a short circuit, then an open circuit. It's still open. There is no current that can flow. And again, here you have 1. This is inverter, you will have 0. If you have 1, 0 now, let's do another color. 1, 0. It is just the opposite. 1 here, so again, this will be open. But 1 here, this will be short. And again, you have a pass. And again, 1. And here will be the opposite. So we have 1, we have 0. So this will be short. This will be open. Again, since you have an open in series with the short, the overall is open. 1 to the inverter will give you 0 as well. It's inverter. Finally, 1, 1. That's interesting because this is the only different case. So let's remove all of that. And let's do with another color. 1, 1. 1 at the B open, 1 at the B is open. 1 at the NMOS is short, 1 at the NMOS is short. So you have a path from the ground to the gate here. So the gate now has 0. And then you have an inverter, so you have 1. So 0, 0 give us 0, 0, 1 give us 0, 1, 0 give us 0. Only at 1, 1, we have 1. We got 1. That's an AND gate. How about in between here? Let's check, or let's assume there is another output called Y1. Let's check the values of Y1 at each Y. In the first 3 cases, Y1 was 1. And in the last case, it was 0. Just look Y and Y1. What is the relation between them? This is basically inverted, right? So this is called not AND. Or simply, this is NAND, which is another logic gate. So that part by itself, let's highlight it. That part here by itself is a gate called NAND. NAND gate. And add inverter to it, it will be AND. Because not AND is AND. Because not will cancel each other. So that's the AND. Let's see the OR. The final example here. This should be the OR, an OR. And let's also do Y1 and Y. Let's put 0, 0, the first case, 0, 0, 0, 0. 0 at the BMOS is short. 0 at the BMOS is short. 0 at the NMOS open, open. So you have a path between Y1 and the high voltage here. So you have here Y1. I'm sorry, you have here at Y1, you have 1. And that's again inverter. So the output will be 0. So that will be an OR gate, and this is the simplest, which has two inputs. This is the symbol for the OR gate. Let's have another example. Let's do 1, 0. 1 at A, 0 at B. 1 at A, 0 at B. 1 on the BMOS is open. So even if this is a short, because there is a 0, you have a short in series with open, so the rest, it's open, still open. It will be something like this, short, then you have open. So again, no current will flow. Let's check the NMOS transistors in the bottom here. You have 1 at the A, so that will be short. This is still open, but still you're gonna have a path between Y1 and the ground. So there is a 0 here. 0 at the input of the inverter will give you 1. I'm sorry, 0 at, yes, 0 at Y1 will give you 1. If you do 0, 1, it will be the same. And again 1. Let's do the Y1, the 1, 1 case. Let's remove all of that. Let's do the 1, 1. 1, 1, 1, 1. So 1 at the BMOS will be open, open, short, short. Again, there is a path between Y1 and the ground. So again, we'll have 0 here. And again, you will have 1 at the output. Okay. If you look, this is an OR gate. And compare Y1 and Y, they are inverted. They are opposite to each other. If this is 1, this is 0. If this is 0, this is 1. So this is basically not OR. Or you can call it NOR. So that by itself, let's do it, or let's have it like this. That part of the circuit by itself is called NOR gate. And it's interesting that you can get the NOR. Okay, and from the NOR we get the OR. Okay, it's not, it was not the opposite. So basically, when we think about the logic, okay, we get the logic first OR and 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 not. But in the implementation, you cannot get the NOR, I'm sorry, you cannot get the OR and the AND directly. You should get first NOR and NAND, then you invert it using the inverter. Okay, guys, that was basically it for this part of the lecture. Thank you very much, and see you in the next video. Bye-bye.